In this topic, we're going to talk about a new technique called multi-objective linear programming. The objective of this technique mainly is to deal with problems that have multiple objectives. So it's similar to another technique called goal programming. The difference is that in goal programming, we already know the right-hand side values for our goals. In this new technique, in multiple objective linear programming, we need to calculate these right-hand side values. In other words, these target values or goals. And then we have to set up what we call as an objective, the minimax objective. So we're going to define this and we're going to talk about the benefits of using this technique. The multiple objective linear programming problem is an LP problem that has more than one objective function. Right? It is viewed as a special type of goal programming problem because we are using goals in a sense here. However, we have to determine the target values of each of the goals. In a goal programming formulation, we use deviational variables. In here, we don't use deviational variables. We use a technique that we'll go over in the next few slides to calculate our right-hand side values for our goals, our target values. Okay? And after we do that, we use what we call a minimax objective, which is basically minimizing the maximum deviation from any of the goals. So for example, if you look at this figure in here, we have that value q. Okay, so that q in here for each of the three constraints specified here is going to specify a maximum deviation. Okay, so the deviation for goal number 1, it's going to be has to be less than or equal to that q parameter for the d1 minus, and for the d1 plus as well. We're going to have another q parameter in there. And the same thing for d2 negative. It's got to be less than or equal to a q parameter. So these, when we formulate this, or we specify this, for example, in Excel solver, you will see this more clearly. Basically, these are going to be variable cells. So the simplex algorithm is going to help us to identify that. Okay, and at the same time, we're going to be using that as our objective function. So that's why it says minimax. So it's minimizing that objective, pretty much that is based on the maximum deviation from any of the goals. And again, we'll see this more apparent in the next few slides through an example. Before we move forward, let's talk about the concept of dominated versus non-dominated solution. Okay, so consider the following. Here, what we see is a hypothetical example of potential trade-offs between profit and amount of toxic waste. So we have two performance measures of interest, or two objectives. Okay, obviously you will like a solution in here that will minimize toxic waste and at the same time maximize profit. So this is a typical example of problems where you have conflicting objectives. Okay, so assume that this curve here shows potential solutions to a problem, to this particular problem. Okay, so let's say, for example, that you have a solution A. Okay, solution A in this case is clearly undesirable because B and C clearly provides better solution. Okay, and what I mean is, for example, solution A will give you this amount of toxic waste and will produce this amount of profit. Well, if you compare that to point B, which is a solution in here, you will obtain the same amount of profit at a much less toxic waste. Okay, so B is clearly a better solution than A in this sense. Okay, solution C actually will provide a solution that will give the same amount of toxic waste, but at the same time will give you more profit. Okay, so C clearly is better than A. So when you have something like this, we can say that B and C clearly dominates our initial solution, or the one that we were thinking about, which is solution A. Okay, and to formally express this, we say that in multiple objective linear programming, a decision alternative is dominated if there is another alternative that produces a better value for at least one objective without worsening the value of the other objectives. And why is this important? Because in our multiple objective linear programming technique that we'll be discussing here, we are going to guarantee that solutions are non-dominated. So let's go through an example to show multiple objective linear programming as a technique. Lee Blackstone is the owner of the Blackstone Mining Company, which operates two different coal mines in two counties, Wythe and Giles, which are located in Southwest Virginia. Due to increased commercial and residential development in the primary areas served by these mines, Lee is anticipating an increase in demand for coal in the coming year. Specifically, her projections indicate a 48-ton increase in the demand for high-grade coal, a 28-ton increase in the demand for medium-grade coal, and a 100-ton increase in the demand for low-grade coal. Okay. To handle this increase in demand, Lee must schedule extra shift of workers at the mines, and it costs $40,000 per month to run an extra shift of workers at the Wythe County mine, however you want to say that, Wythe, and $32,000 per month at the Giles mine. Only one additional shift can be scheduled each month at each mine. The amount of coal that can be produced in a month's time at each mine by a shift of workers is summarized in this table in here. Okay, so for high-grade type of coal in the Wythe mine, they can produce 12 tons, and in the Giles mine, they can produce 4 tons, and so forth. Okay, for medium grade, Wythe can produce 4 tons, and we can produce 10 tons of low grade, and Giles can produce 4 tons of medium grade and 20 tons of low grade. Unfortunately, the methods used to extract coal from these mines produce toxic water that enters the local groundwater aquifers. At the Wythe mine, running an extra shift will generate approximately 800 gallons of toxic water per month, whereas the mine at Giles County will generate about 1,250 gallons of toxic water. Although these amounts are within EPA guidelines, Lee is concerned about the environment and doesn't want to create any more pollution than is absolutely necessary, of course. Additionally, although the company follows all OSHA safety guidelines, company records indicate that approximately 0.2 life-threatening accidents occur per shift each month at the Wythe mine, whereas 0.45 accidents occur per shift each month at the Giles mine. Lee knows that mining is a hazardous occupation, but she cares about the health and welfare of her workers and wants to keep the number of life-threatening accidents to a minimum. Okay, notice again that she would like. Okay, and you see that all around. There's of course a couple of hard constraints in here. So we'll see what we see here is a combination of hard constraints and goals or would likes. Okay, so in other words, this is that, and we'll define this more clearly in the next few slides. Okay, so let's move on. So let's do a quick summary of the problem statement. So Blackstone Mining runs 2 coal mines in Southwest Virginia. Here we show monthly productions by shift of workers at each mine. Okay, each of the different types of coal that can be produced at each of the 2 mines. Blackstone needs to produce 48 more tons of high grade, 28 more tons of medium grade, and 100 more tons of low grade. Okay, so this is a summary of the long problem statement that we just saw. So let's define the decision variables. Let's talk about objectives and hard constraints. Okay, so the problem statement specifies that the decision to be made here is to find out the number of months to schedule an extra shift at the Wythe County mines, where that I is 1 for Wythe and 2 for Giles. Okay, so what are the objectives in these problems? Well, we have 3 main objectives. Okay, the first one is we want to minimize production costs, which is specified by 40x1 plus 32x2. The second one, we want to minimize the amount of toxic water produced, 800x1 plus 1250x2. And the third one, we want to minimize the number of accidents. Okay, so that's specified by that linear function, 0.2x1 plus 0.45x2. Okay, so what are the hard constraints in this problem? Well, we have constraints on the high-grade coal that's required, and we specify that as 12x1 plus 4x2 is greater than or equal to 48. We have a constraint on the medium-grade coal required, and we specify that as 4x1 plus 4x2 greater than or equal to 28. And we have a low-grade coal requirement as a constraint as well, which is 10x1 plus 20x2 is greater than or equal to 100. And of course, we cannot forget our non-negativity constraints. Okay, so both of our variables have to be greater than or equal to 0. Okay. If the objectives had target values, we're going to call these target values T1, T2, and T3 for each of the 3 objectives. We can just treat them as 3 different goals, right? So we can say goal number 1, which relates to the objective number 1 of total cost. Say the total cost of production should be approximately that T sub 1, okay, the target value for that goal. we can say for goal number 2 that the amount of toxic water produced should be approximately that T sub 2 value, or that target goal for that objective. And goal number 3, you can say the number of life-threatening accidents should be approximately T sub 3, or a target value for that goal. So in multiple objective linear programming, what we do is to find out the values for T sub 1, T sub 2, and T sub 3, we solve 3 separate LP problems. Okay, so the linear programming number 1 will be to solve an LP problem that optimizes that goal number 1. And I'll show you in the next slide how to set this up in Excel, and you probably see it more clearly. But if you think about it, if we're talking about linear programming, we usually see one objective. So in other words, the objective in here will be to optimize that goal number 1. Okay, and if we find that optimal solution for using that as our objective, the total cost, we can actually just set that optimal function value to be equal to T sub 1. Okay, and the same thing for the second and third objectives. So linear programming problem number 2 would be to solve an LP problem that optimizes G2, okay, or goal number 2, which is the amount of toxic water produced. Okay, so what we're doing here is just we can set up as a single objective to optimize this goal 2 objective, and the objective function value will then be set to be equal to T sub 2. And the same thing for T sub 3. Okay, so the third problem will be to solve an LP problem that optimizes that third goal, which is the number of accidents. Okay, again, the objective for that single LP would be to optimize this objective. Okay, and the objective function value, we can set that up to be equal to T sub 3. So that's the main idea behind multiple objective linear programming. So let's see this through. Let's see how we implement this in Excel, and hopefully you can see it more clear. Okay, so let's look at a spreadsheet implementation to solve that first linear programming problem to get the value for T sub 1. Okay, so let's say we have this spreadsheet formulation for it. Okay, notice that our decision variables in this problem are specified by B5 and C5. Okay, so still we have so this area here, this cell is going to correspond to your X1, and this one is going to correspond to X2. So B5 is X1 and C5 is X2. Okay, those are our decision variables. Okay, the coefficients of the decision variables are B8 and C8. Okay, and notice that what we're doing here is just running a simple LP formulation. Okay, so we want to find an optimal solution that solves for that objective, cost per month. Okay, so our objective function is going to be specified at this cell right here. Okay, so the objective function in this case is going to be 40x1 plus 32x2. So you specify that as 40 times B5 plus 32 times C5. Okay, so we're going to have a single objective function, which is going to be in this cell. Okay, these are not going to be objectives. Okay, because what we're doing is running independent linear programming problems to find out maximum values or goals for our objectives. Okay, so these two parameters for the second and third goal. The second goal has to do with toxins per month, which is going to be here, and the third goal is accidents per month, which is going to be here. They're just going to be solved based on whatever values are obtained here for our decision variables for this constraint, for this objective. Okay, so we run this formulation. We want to optimize this parameter, and whatever the resulting variables to optimize that parameter, we're going to use to calculate that second and third goal. Okay, this area in here is the left-hand side value of the 3 hard constraints in our problem. Remember, we have one for high-grade coal produced. It's going to be calculated in here. The medium grade and the low grade are going to be calculated here respectively, and these are the right hand side values for these hard constraints. Okay, notice in here that, again, I repeat, D9 and D10, which are this is the value for goal number 2 or objective number 2, and this is the value for objective number 3. They are not constraints and they're not goals in here. They just get calculated using the resulting decision variables that optimize this parameter. So in this case, these are the resulting decision variables that are used to optimize this parameter, and we just use this to calculate this. So in other words, that 7,625 is going to be 100 times 250 plus 1,250 times 4.5, and so forth. Okay. Notice here that the optimal function value when you're trying to optimize cost per month is 244. Okay, what this is saying is that you cannot get in a solution where you're considering more than one objective, you cannot get a value that is better than 244. And so it makes sense to set 244 as our target value for that objective. Okay? For T sub 2, pretty much we're looking now at the target value for the second objective in our problem, which had to do with toxins per month. So we set up another linear programming formulation, and now we want to optimize our toxins per month, which is that value in there. You notice that the objective function value when we attempted to optimize that cost parameter was 244. Now, if we don't care about that as an objective, if we just want to optimize this second objective here, toxins per month, notice that it yielded a worse cost. Okay, instead of 244, it's 256. However, it reduced the toxins per month. Okay, so again, it's the same thing. Our objective here is to optimize this parameter, to minimize these toxins per month. Everything else stays the same. Okay, so the accidents per month and the cost per month, they're not constraints, they're not objectives in this particular formulation, because all we are doing is trying to find out the target for goal number 2. Okay, so in this case, the target for goal number 2, for objective number 2, is going to be 6,950. Okay, so we already set up T sub 1 in the previous slide. Now we set up the target value for goal number 2, and if we do the same thing for target number 3, so we'll run another linear programming formulation, and in that case we will attempt to optimize only this accidents per month objective. If we do the same approach, we're going to find out that T sub 3, it's set at 2. Okay, so we have our target values. Target value T1 is going to be 244. T2, target 2 is going to be 6,950, and target number 3 is going to be 2. This graph shows the solutions for each individual problem that we just solved. Okay, so what we see, since we solved 3 different problems, we're going to see solutions to our 3 based on our 3 objectives. Okay, so this is solution point number 1, which minimizes production costs. This is solution point number 2, which minimizes toxic water, and this is solution number 3, which minimizes a number of accidents. Okay, we already determined the levels of cost, toxic water production, and expected accidents rate that are offered by this solution. So if none of these solutions are acceptable, then the decision maker may wish to explore other non-corner point or non-feasible feasible solutions, but non-extreme point solutions. Okay, so maybe the decision maker will be better off by selecting a non-extreme point solution, so a solution that is around this area, or another solution that is at this point, or another solution that is at that point. Okay, so by calculating these extreme points, it gives us some idea about the solution at those points, and then the decision maker must decide whether he or she is happy with that solution or not. If he or she is not happy with that solution, then we want to continue with multiple objective linear programming to find to examine other points along that feasible edge in here that could give us a solution that is more acceptable to them. Okay, notice here in this table, it gives us the optimal values for each individual solution. Okay, so the solution that aims at optimize that first cost parameter, which was solution number 1, yielded the lowest cost. Same thing, solution number 2 yielded the lowest toxic water, and solution number 3 yielded the lowest number of accidents. So if the decision maker is not happy with any of these 3 solutions, that you want to continue the analysis and find or examine other points along that edge, okay, to find a solution that is acceptable to the decision maker. Okay, so let's define the goals and objectives of this problem now that we have defined targets for each of our objectives. So these targets are going to be used now to set up 3 different goals corresponding to each of the different objectives in this problem. So goal number 1, total cost of production should be approximately $244, okay, because that was our value for T sub 1. Goal number 2, the gallons of toxic water produced should be approximately 6,950, because that was the optimal value that we obtained for T sub 2 when we run that second LP problem. And goal number 3 is the number of life-threatening accidents should be approximately 2. Again, because that was the optimal function value that we obtained when we ran that individual third linear program. Okay, so for this objective, we can do something. We can minimize the sum of percentage deviations. Okay, and if we decide to do that, we can use this function. Okay, minimize the sum of percentage deviations. So we're going to have a weight parameter associated with each of the deviations from each of the goals, and we have a target value. Okay, so it's gonna, that's how we get that percentage deviation. Okay, and that's for goal number 1. For goal number 2, again, is the same thing. We're gonna have a target parameter. So whatever value we get, we're gonna divide it. This is gonna be our deviation, correct? And we're gonna divide that times the target value, and there's going to be a weight parameter associated with that. We've mentioned already that typically we'd start off setting each individual weights to 1, and then we use that as an initial assessment, and then we continue from there. Okay? And again, for goal number 3 is the same thing. This numerator represents deviations from the target, and this is the target value, so this gives us a percentage deviation, and we have weight in here, so it's a weighted percentage deviation. Okay, this is basically a linear combination of the decision variables. Okay, therefore, this objective, if you remember, the graphical solution to the 2-variable problem, it's only going to be the optimal solution in here is always going to be an extreme point. Okay, so in this case, we have 1, 2, 3, 4 extreme points, and we already evaluated all these extreme points, at least solution 1, 2, and 3. And we've already decided that the decision maker is really not too happy about it. So we already know the solutions to those points. So we need to find another way, another objective. We need to define another objective that will allow us to explore non-extreme feasible solutions. Okay, and for this, we will use what we call the minimax objective. And basically, the minimax objective can be used to explore other points at the edge of the feasible region in addition to the extreme points. So it can look at points along this edge, and it can evaluate points along this edge to let us know whether we are happier to present another solution and let us determine whether the decision maker is happier or not with them. Okay? So this is a specification of the minimax objective. Here our objective is going to be to minimize, let's just call this Q, this quantity, okay, subject to additional constraints. These constraints are again the deviations. These are the weighted deviations from the target goals. This in here, the target goal is 244. That's for goal number 1, okay, and that's going to be less than or equal to some parameter. Okay, so what we're doing in here is minimizing the maximum weighted percentage deviation from the target values of each of the goals. Okay, and again, hopefully this will make more sense when we show the Excel formulation for it. Okay, but basically this is what it's doing. Okay, so for these are going to be the additional constraints for the 3 objectives now, or we call it 3 different goals. In here, these 3 Q values are going to be selected by the simplex algorithm. Okay, so when you're setting this up in Excel, in Solver, in Excel, these values are going to be part of the variable cells. Okay, so the algorithm is going to find optimal solutions in here. Okay, that's going to minimize those values as well. So we're minimizing the maximum deviation. Okay, so it's pretty cool. So we'll see this in action through an Excel example. Okay, or formulation for this. Okay, basically, this approach allows or lets you explore non-extreme point solutions as well. So it's pretty powerful. This is the final formulation of the problem. Our objective is to minimize the maximum deviation. Okay, so it's going to minimize maximum deviation from the goals, and these Q parameters, or the deviations, are the right-hand side values for each of our constraints. Okay, so we have our 3 hard constraints related to high-grade coal requirements, medium-grade coal requirements, and low-grade coal requirements. Then you have our goals in here. These are deviations. These are weighted deviations, and percentage if you divide it by the target value, okay, of 244 in this case. Okay, so this is the goal number 2, so it's the minimax constraint for goal number 2. And what makes it again a minimax is that we want to minimize, our objective function is to minimize that Q parameter, and these all represent deviations, okay, from this goal. So we want to minimize the maximum deviation from the goals. Okay. We have our non-negativity constraints as well, x sub 1 plus x, and x sub 2 is greater than or equal to 0. And we have also non-negativity constraints for each of our weights. Okay, again, we'll start by setting these weights equal to 1, and then we'll go from there. We'll examine the solution and see if we need to increase those weights. Okay, so here's a snapshot of the Excel implementation for this problem. Okay, I added comments in here to hopefully make it easier for you to understand. Each of the comments in here has the formula, the specific formula that we use for a specific cell in Excel. So this sum product formula is the formula that was used for this cell in here. Okay, so when we run this problem, of course, it's going to have a value that is not 0. It's going to be something greater than 0, and hopefully greater than or equal to 48. Okay, this formula here, for example, is the formula that was used to represent this cell in here, and so forth. Okay, so notice that the values for H9, H10, and H11 are both the same, F4. Okay, and F4 here represents that objective function value. Okay, so we want to be able to minimize this objective function value. Okay, these represent in here, these are constraints for the deviations. Okay, so we're going to treat this as changing variables as well. So we'll see in the next slide the solver formula snapshot for this and how to set this up. But basically, this objective function cell is a variable cell, which is represented by here, H9, 10, and 11. In other words, Excel, the simplest algorithm, is going to try to find an optimal parameter in here. It's going to find the maximum deviation possible, okay, for each of these 3 constraints. And our objective is to minimize that maximum deviation. Okay, so it's pretty cool in a way that this objective function cell is both a variable cell, because these all call upon that. So these are all F4, and at the same time, it's an objective cell as well. Okay, so how do we calculate, for example, this left-hand side of the constraint? This is pretty straightforward. It's what we've been doing all along. This is a hard constraint, so this is going to be 12x1 plus 4x2. Okay, so it's the sum product of those 2 cell areas, cell regions, and it's greater than or equal to 48. Okay, the same thing for that constraint and that constraint, because these are 3 hard constraints. Okay, no tricks in there. Okay, the constraint here, which is going to be pretty much the value for our goals, is represented by this formula in here. Okay, and basically what this is the weight for that goal number 1, E14. So E14, I set up a table with weights for each of the goals. So that's the weight times the deviation, which is represented here, over the target value. Okay, D14 in this case, which is D14. That's the target value for goal number 1. Okay, and the same approach is used for F10 and F11, which represents the left-hand side of goals 2 and 3. Okay, so all I'm doing here is just representing the formulation that was developed for this problem. So this is how you set up the solver solution. I included in here a snapshot of solver to make it easier for you guys to understand it and hopefully replicate this at home when you're studying this. Okay, so our objective cell in here is going to be that F4. Again, notice that F4, these values here are going to be the same values. This is actually the solution to it. So we formulate it and we solve it, and it yielded this solution. Okay, notice that these values are only are like pointers to that cell in there, so they're all going to be the same values. Okay, it's a minimization problem. Our changing cells are C4 and D4, C4, D4, and F4. Okay, so this is a changing cell as well, so it's a variable cell. Okay, so it's a variable cell and it's an objective function as well. Okay, so this is the unique aspect of multiple objective linear programming formulations. Okay, the constraints, this is pretty straightforward. These are greater than or equal constraints, so we have those greater than or equal constraints in there, and then we have 3 less than or equal constraints, and we are representing them with that, and we make sure that we select non-negativity constraints and the simplex algorithm, and we run our solution. And yielded an objective function value of that, and more importantly, yielded values for our decision variables, x1 and x2. So it's a pretty neat technique, and again, the key here is to understand that you are using that objective function and setting it up as both a changing cell and an objective function cell as well. We initially set this up such as the weights for each of the three different goals were set up to 1. Okay, so the solution that we obtained in the previous slide was with W sub 1, W sub 2, and W sub 3 equal to 1. We saw that. Okay, different weights produce different solutions. Okay, so the key of this is understanding that the decision manager, decision making, can explore various solutions that do not necessarily occur at extreme points of the original feasible region to the problem. Okay, so it doesn't only explore the solution at that point, or that point. It explores different solutions, and that's the beauty of this technique. Okay, notice how changes in the weights cause different possible solutions. Okay, and they deviate from the extreme points. For example, in this solution, W sub 1 is set up to 10, so the weight for goal number 1 is increased. Okay, so it's prioritized at a higher level by a magnitude of 10. So that weight for goal number 1 is set up to 10, and the rest are set up to 1. Okay, when we solve this problem, it gives us decision variable values specified here. Okay, so the solution is moving. What we're doing here, if this is the optimal solution, that point is the optimal solution when you're considering only goal number 1. Okay, now we're considering also goals number 2 and 3, but it's moving closer to that optimal solution because we prioritize it higher. Okay, notice solution number 2 here. It increased the value. We increased the value of the second goal, so it's going to be close to that second optimal solution, to that second extreme point in here, because this extreme point right there represents the optimal solution when you're considering only a single objective, that second objective. Okay, and notice if you just increase the value of weight number 3, the solution keeps moving more towards that objective function value representing the maximum objective when you're considering that goal number 3 as a single objective. So you can see how solutions will go around this edge along the line, and that's one of the benefits of it, that we can adjust these weights and we can find solutions that are better in terms of what the decision maker would like to see. A few comments about multi-objective linear programming. This is important to understand. For minimization objectives, the percentage deviation is what we just saw, what we just used, actual minus target over target. However, for maximization objectives problems, the percentage deviation is target minus actual over target. And if the target value is 0, use the weighted deviations rather than the weighted percentage deviations. Finally, a summary of multiple objective linear programming are a series of 9 steps. Step number 1, identify the decision variables in the problem. Step number 2, identify the objectives in the problem and formulate them as usual. Step number 3, identify the constraints in the problem and formulate them as usual as well. Step number 4, you solve the problem once for each of the objectives identified in step number 2 in order to determine the optimal value of each objective, because you're going to use that, step number 5, to specify their target values. Okay. Step number 6, for each goal, create a deviation function that measures the amount by which any given solution fails to meet the goal. Step number 7, for each of the functions identified in step number 6, assign a weight to the function and create a constraint that requires the value of the weighted deviation function to be less than the minimax variable q. Step number 8, solve the resulting problem with the objective of minimizing q. And lastly, inspect the solution to the problem, and if it is unacceptable, then adjust the weight. So go back to step 7 and 8. Okay, so this is a summary of how you implement, or step-by-step process to implement a solution or formulate a solution for multiple objective linear programming.